In this video we're going to be having a look at digital counters. Now a counter is a digital circuit whose output progresses in a predictable, repeating pattern, as you'd expect as a counter. It advances one state or one count for each clock pulse, normally. When we talk about counters, we talk about the count sequence, and the modulus, and the direction. The count sequence is the specific series of output states through which a counter progresses. The modulus is the number of states a counter sequences through before repeating. Sometimes it's known as mod n, and the direction being either an up counter or a down counter. So let's have a look at a quick example. If I was to concatenate 3 D flip-flops together, in this fashion, and then pull off lines in between, we would end up with a counter like this. So I'm going to call this one QA, QB, and QC. And what we're actually going to find is that this is the most significant bit and this is the least significant bit of our counter. Now it's a 3-bit counter, so I know the maximum value that we're going to be able to count up to is we'll have 8 states, but the max number is equal to 2 to the n minus 1, which in this case equals 7. So we're going to be able to count from 0 to 7 repeatedly. Alright, this would be known as a mod 8 counter. So let's have a look at the timing diagram. 1, 2, 3, 4, 5, 6, 7, 8, and 9 for good luck. So there's our clock pulse, and let's assume that it is rising edge triggered. QA, QB, QC. We're going to look at the falling edges in this example. So toggle, falling edge, toggle, 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 toggle. So straight away we see that divide by 2 behavior. The frequency has halved. Following the falling edges along again, toggle, 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 toggle. Following our falling edges, toggle, toggle. Now, if we write down the binary associated with each state, we'll start to see a pattern. Oh, 1 0 1 0 1 1 1 1 1 0 0 0. if I write down underneath the number in binary, 0, 1, 2, 3, 4, 5, 6, 7, and then back to 0, you can see how we've made a counter. And you can see that frequency division, this is half the frequency of the clock, B is half of A, and C is half of B. What we've done is if we read out across the outputs of each of our, these could be JK flip-flops set up to toggle, we see that we end up with a up counter. It's got 1, 0 to 7, so it's got 8 states, so it's what's known as a mod 8 counter. If I was to draw the state diagram for this, now I can do that in binary or decimal. Let's do it in binary. 1, 0, 1, 1, 1, 0, 1, 1, 1. So we get 1, 2, 3, 4, 5, 6, 7, 8 states. That was a bit poor. That one, that one, that one, that one. 4, 5, 6, 7. And arrows between them showing how the count sequence progresses. So remember that count sequence is one of our definitions. So count sequence is shown by the state diagram. And the modulus, based on the number of bits we've got, and the circuit, so in this case mod 8, based on the fact we're counting all the way up to the maximum value, 7, and then going back to 0, and then a direction, in this case it is counting up, as per the diagram. Let's have a look at how a counter would actually be constructed. So in this case I'm going to create a slightly more complicated counter using 4 JK flip-flops. J, K, and our clock inputs. And the output, Q, is going to cascade from one flip-flop to the next. We're also going to use the clear input so we can reset our counter at any point. So here's our clock. And I'm going to do something a little bit interesting here. I'm going to have a AND gate. Oh, that was a bit wobbly. At the end here. And we'll see why shortly. But it's going to be connected to each of our clear inputs. All our J and Ks are going to be connected to logic 1. So they are all connected to in a toggle fashion, like so. Just do dots to make it a little bit easier to see what's joining and what's not. And we're going to bring out our counting bits from QA through to QD. And I'm going to connect a couple more of these to my AND gate. In this case, QA, QD, and the clock all connect to my AND gate. So let's have a look how this circuit functions. As we expect, just like we've seen in the previous example, this all clocks through, providing a counting pattern. But when, let's have a look at this AND gate, when this is a 1 and this is a 1, those could be 0. Alright, so that would be, remembering this is the most significant bit, 1, 0, 0, 1 equals 9 decimal. Alright, and we get a clock pulse, rising edge, all counters reset. Therefore, counter goes from 0 to 9. It's what's known as a decade counter. It's asynchronous because the clock inputs cascade into each other, and because of the fact that we have asynchronous inputs connected. It would only be a synchronous counter if the same clock line connected to the clock inputs of all flip-flops. Alright, and sorry, I should have my falling edge falling edge detection for the JK flip-flops here to get this to function as we saw here. So this will continue counting with the 4 bits until the diagram reached the stage 1001, at which case then all the outputs would be reset to 0 at the next clock edge, which is why this also comes through to the AND gate. Then it continues counting again from 0. So our state diagram would go from 000 through to 1001 and then back round again. Alright. Also, I'll just quickly draw for you what a synchronous counter will look like. Okay, just so you can get a feel that they are a little bit more complicated. So it'll be 1 and 1 on our J and K. Okay, we're still doing a toggle. But our clock input is now connected all in parallel. That was a pretty rough line. There we go. Alright, so we see this parallel clock line. And if we have that with no asynchronous inputs, this is now a synchronous counter. But it's actually much harder to design the circuitry for in order to get it to reset at a particular value. Quite often you end up with XORs and a few other more complicated configurations. Right, but synchronous, the clock lines are all joined together in parallel. Asynchronous, we see the clock line is cascade from the output of one flip-flop into the next, which is why it's also sometimes known as a ripple counter, and the fact that we're using this asynchronous input, right, is what makes it asynchronous. So, quick summary. Digital circuit. A counter is a digital circuit that's output regresses in a predictable repeating pattern. Advances one state for each clock pulse. State is basically one of these bubbles in our state diagram, one value of the counter. We went through the count sequence and modulus, and the modulus is basically how many count states do we have. 0 to 7 is 8 states, okay, 0 to 9 is 10 states, and so forth. We had a look at state diagrams, what an asynchronous counter might look like. This one's actually known as a truncated counter because of this bit here. It doesn't count up to its maximum value, so this one would be a mod 10 counter. It's got 10 states from 0 to 9, and very briefly just had a look at synchronous counters.